Hello everyone, this is Swati from Aeronautical Engineering. So today we are here for the tech talk topic, non-linear evolution of shear flows in double tearing modes. Introduction to shear flow in aircraft structures. Shear flow are internal forces that occurs in aircraft structure when they are subjected to aerodynamic loads. This flow play a critical role in ensuring that wings, fuselage, and control surface remain stable under flight conditions. When analyzing complex aircraft structure, it becomes important to understand how shear flow behave under nonlinear and dynamic conditions. One such complex situation arises in the presence of double tearing modes, which introduce instability in the system. Studying the nonlinear evolution of this shear flow helps engineers predict failure mechanisms and design for more robust aircraft structure. Understanding double tearing modes are the type of magnetic instability originally studied in plasma physics, but also relevant in mechanical and structural dynamics. In aircraft structures, similarly behave can occur in layered or composite materials, where two distinct shear forces interact. The layers can tear or shift relative to each other, generating coupled shearing instability. When these two tearing zones evolve together, the interaction between highly nonlinear and may lead to structural damage if not controlled. Double tiering modes helps explain how localized shear distribution evolved in more significant stresses concentrations within aircraft components. Role of nonlinearity in structural behavior. In real world conditions, the response of aircraft structures to external loads is often nonlinear. This means that the relationship between the loads and deformation does not flow. A sample. Straight line pattern. When double tearing modes are present, nonlinear effects become more prominent and harder to predict. The nonlinearities can cause unexpected stress redistribution, large deflection, or even resonance. Understanding this behavior is crucial in aircraft designs as engineers must ensure that structures do not experience sudden failure due to complex interaction between shear layers and external force. Mathematical modeling of shear flow. To analyze the nonlinear evolution of shear flow in DTMs, mathematically models are used. These models rely on equations from fluid dynamics, solid dynamics, and nonlinear differential equations. By modeling the interaction between two shear layers, researchers can simulate how energy is transferred, how deformation evolves over time, and under what condition failure might occur. Advanced computational tools are often used to solve these equations to analytical solutions are rarely possible. These models form the foundation for understanding the impact of DTM in aerospace structures. Computational tools and simulation techniques. Computational tools like finite element analysis, computational fluid dynamics, and key in studying the nonlinear behavior of shear flows. These tools help simulate real-world scenarios such as deformation of aircraft wings under turbulent flow. For DTM simulations must be very detailed, capturing the interaction between multiple shear zones and nonlinear responses over time. Adaptive machining and time-stepping algorithms improve accuracy when these tool engines can predict how small cracks or defects may evolve into larger structural problems under repeated stresses and vibrations. Material consideration in shear flow analysis. Material used in aircraft structures such as aluminum alloy and composites behave differently under nonlinear shear loads. Some materials may absorb energy and resist tearing, while others may be more brittle and and prone to be failure. The presence of double tearing modes means the certain layer of interfaces in the material may slide or delaminate. Engineers must study how different materials respond to this effect. Choosing the right material with high fatigue strength and shear resistance is essential for preventing cracks propagation in double tearing regions. Energy transfer in energy transfer and instability mechanism. In systems affected by double tearing modes, energy can be transferred between different parts of the structures in complex way. As one tier layer begins to shift, it can induce motion in the second layer, amplifying the instability. This energy exchanger leads to sudden increase in local stress known as shear shocks. These surgeons can trigger buckling, cracking, or complete structural failure if not properly managed. Understanding how energy is stored, transferred, and released helps in predicting the onset of critical failure modes in aerospace components. Experimental validation of models. While simulation provide uh, valuable insights, experimental testing is necessary to validate models of nonlinear shear flow evolution. Scale down models of aircraft panels or fuselage sections can be tested in labs using controlled shear loads. Sensors capture data or display stresses distribution and crack growth. Comparing this data with simulation helps refine the models to improve prediction accuracy. This experiment can critically, especially in safety critical aerospace application, this accurate failure prediction can save lives and reduce maintenance cost. Influences of geometric imperfections. Real world aircraft structures are not perfectly uniform. Small geometric imperfections such as slight bending, dents, can greatly influence the behavior of shear flow under DTM conditions. These imperfections may act as initial points for tearing or change the direction of stresses propagation. During nonlinear evolution, such imperfections may grow and interact in an unexpected way. Engineers must account this in both design and analysis stages, including tolerance limits and safety margins in structural design helps mitigate the risk proposed by these real-world derivations. Interaction with other structural loads. Aircraft structure experiences not just shear forces but also bending, torsion, axial loads. The interaction of those forces with nonlinear shear flow can lead to complex failure scenarios. For example, a bending load might be weakened a shear interfaces triggering a DTM behavior. Similarly, torsion could amplify shear instability in composite materials. Structural analysts may therefore consider combined loading effects, especially during maneuvers, takeoff, or landing. Where stresses peak, multi-axial loads simulations are essential to understand how different forces components influences the evolution of shear flow. Time-dependent behavior and fatigue. Over time, repeated loads can cause fatigue in aircraft structure, especially in areas to double tearing. Even small shear fluctuations can accumulate damage in joints, rivets, or composite layers. Time-dependent or creep behavior is particularly important in high temperature environments. Nonlinear evolutions of shear flow can relate in slow but continuous material degradation. This means that aircraft components may appear fine under inspections but failure under sudden loads due to internal damage accumulations. Predictive maintenance models are being developed to track such changes and prevent unexpected failures. Importance in composite structures. Modern aircraft increase Modern aircrafts use composite materials, which are made of layer structure bonded together. These layers can behave like double tearing zones under shear stress. That interface between layers are particularly vulnerable to delamination when exposed to DTM-like behavior. Analyzing how shear flow involves non-linearly in such materials helps engineers design better layups and bonding techniques. Damage tolerant design principles and smart materials that can self-monitor or even heal are being researched to address these challenges and improve structural longevity in composite aircraft parts. Design strategies for structural safety. To minimize the risk proposed by nonlinear shear flow evolution, aircraft designers use safety-focused strategies. This includes designing redundant load paths using damage-tolerant materials and placing reinforcement in critical shear zones. Structurals are also tested under conditions that simulate DTM behavior to ensure they can withstand unexpected stresses. Real-time health monitoring systems can detect the early stages of tearing or delamination. These strategies helps ensure that even if a part of the structure fails due to nonlinear shear behavior, the rest can maintain overall integrity and protect the aircraft and passengers. Advanced monitoring and detection system. Early detection of nonlinear shear flow involves a crucial for safe aircraft operations. Modern aircraft are equipped with structural health monitoring systems. They use fiber optic sensors to detect changes in stress pattern. These systems can alert maintenance crew to potential DTM like behavior before it becomes dangerous. By analyzing vibration, strain, or sound data, engineers can pinpoint the location of severity of the issue. Integrating SHM with AI algorithms improves diagnosis and reduce inspection, like making aircraft maintenance more efficient to proactive. Conclusion. For conclusion for the future work, they study nonlinear evaluations of shear flow in double tiering modes, offer valuable insights into the complex behavior of aircraft structures. Understanding this topic helps engineers predict failures, enhance material performances, and design safer aircraft. Further research will focus on better mathematical models, smart materials with adaptive behavior, and AI integrated monitoring systems. This advancement aim to detect the respond to structural changes in real time. Ultimately, mastering this field ensures that aerospace structures remains reliable during and capable of handling the extreme conditions of flight with improved safety margins. Thank you.